All right, guys, in this lesson we're going to be reviewing over summarizing distributions. So if we're given this example right here of just a basic data set, the monthly rainfall in Monrovia, Liberia, where May through October is the rainy season and November through April is the dry season, is as follows. And what they do is they give us all 12 months and then the total rain in inches that each one of those months received, basically. And so if we're asked to find our measure of center for this, we can do that in a few ways. So first we can look at mean, which again is just the average value of a data set. Hopefully you understand how to find mean, where it's just adding up each one of the values in our data set and then dividing it by the total number that's in the data set. So all of those numbers added up divided by 12 would give us 15 inches. The second measure of center that we could find is the median, which is the middle value of a data set when arranged in numerical order. So if we're asked to find the median of that, what we have to do is we have to put all of our data in numerical order from least to greatest. And because we have 12 months of data, that's going to give us 6 on the lower 50% and 6 on the upper 50%. So we need to find the two middle values and basically take the average of those, which is 9 plus 16 divided by 2, which gives us about 12.5 inches as our median. So we're asked, our median is actually lower than our mean. So why is the mean higher than the median? Well, that's because we have two pretty extreme values over here at 37 and 31 that actually kind of pull our mean to the right a little bit. We have a lot of low values over here, and then those two rather large values actually make our mean a little larger. So essentially what that means is that the mean is non-resistant to extreme observations, which means that, depending on how high or low some of those upper observations are, that could potentially affect the mean value as a whole. And so that's why when we're describing center, a lot of times we want to use median, because the median is resistant to those extreme values. If you take these two values right here at 31 and 37, you could lower them, you could raise them to 10,000 inches of rain, and it wouldn't really affect the fact that your median is always going to be 12.5 inches. And so that's why we tend to use median a lot more than mean. If we're asked to find the measure of spread, we can do that in quite a few ways as well. We have our range, which is the difference between the highest and lowest value in a data set. We have our interquartile range, which is the difference between the middle 50% of the values in our data set. And again, how we find our IQR, or interquartile range, is by taking whatever value represents quartile 3 and subtracting quartile 1 from that. We also have our variance, which is the average squared distance of all the values from the mean. And then we have our standard deviation, which is the square root of that variance. So again, the variance would be basically this entire formula without the square root of it. But our square root, or our standard deviation, is essentially taking each one of those data sets and subtracting it from the mean itself, adding all of those up, or squaring it, and then adding all of those up, and then dividing it by the total number in the data set minus 1, and then taking the square root of that function right there. So if we're asked to calculate any measure of spread for our problem, if we're asked to find the range of monthly rainfall totals, that range is going to go from 1 inch to 37 inches for a difference in 36 inches per year. If we're asked to give a spread of our distribution, again, most of the time we can just say that the range of rainfall goes from 1 inch to 37 inches. We don't actually have to calculate or do the math in that sense. If we're asked to identify the 5-number summary for our data set and find the IQR of the monthly rainfall totals, our 5-number data set is represented by our minimum, quartile 1, median, quartile 3, and maximum. That's each one of the 5 numbers. So our minimum would be 1, our quartile 1 would be 4, and again, quartile 1 represents kind of the 25th percent, or that 25% of data. And so in this case, 25% of 12 is probably going to be this third data point right here at 4. And so that would represent quartile 1. Our median, it actually is not 9.5, it should be 12.5 in this case. And our quartile 3 is going to be represented by 26. And again, quartile 3 represents that 75th percent of data in our data set. And our maximum is going to be 37. So if we're asked to find the IQR, the interquartile range for that, we would take whatever value represents quartile 3 minus whatever value represents quartile 1, which in this case is 26 minus 4, and that gives us an IQR of 22. Then if we're asked to find the standard deviation of the monthly rainfall totals and explain in context, what we would do is we would take each one of the data points, subtract it by the mean, square it, and then add all of those data points up, continue to do that, then divide it by the total number in the data set minus 1, which is 12 minus 1 is 11, and then take the square root of that, and that gives us a standard deviation of 12.52. So that just takes care of finding the standard deviation of the monthly rainfall totals. If we're asked to explain that in context, what we would say is the average month differs from the mean of 15 inches by about 12.5 inches of rainfall. We can also kind of find our outliers using a pretty particular formula if we're given an entire data set. So outliers are basically just an observation that lies far outside the pattern of the other values in the data set. If we are asked to find what numbers in that data set are potentially outliers, we have to use these two formulas right here. So an outlier is essentially any number that is less than quartile 1 minus 1.5 times the interquartile range, or any value that is greater than quartile 3 plus 1.5 times the interquartile range. And so if we're asked, are there any months where rainfall would be considered an outlier, what we would do is we would take our quartile 1 value minus 1.5 times 22, and that gives us a value of negative 29. And then our quartile 3 value of 26 plus 1.5 times the interquartile range of 22, and that gives us a value of 59. And we determine whether there are any values that are less than negative 29 or any values that are greater than 59. And since there are no values below negative 29 and no values above 59, there are no outliers in this data set. We also have measures of relative position. So that's essentially the z-score, how many standard deviations an observation is from the mean of a data set. This is also known as the standardized score as well. So our z-score is whatever value that we're asked in the question minus the mean divided by the standard deviation. So let's say that we're given this example right here, where the number of calories in 12-ounce servings of 5 popular beers are 95, 152, 188, 205, and 131. If we enter all of those values into stat edit in our calculator and then hit stat and arrow 1 over to the right for calc, and then click number 1 or press number 1 for one variable statistics, we're given our mean of 154.2, we're given a couple other numbers, and we're given a standard deviation of 44.076. So if we're asked a question, if we sampled a new beer with a calorie content of 196 calories, where is its relative position in the data set, or where is its standardized score in the data set? Something along those lines, then we would need to calculate for Z in this case. So again, we're given a value of 196 calories, so we would take 196 minus our mean of 154.2, which we found right here, divided by our standard deviation of 44.076 to give us a z-score of 0.9484. So we would say in context that the new beer is approximately 0.95 standard deviations above the mean of 154.2 calories per 12 ounces. Okay. We also have this idea of an empirical rule. And so the first thing we need to know about the empirical rule is a normal distribution. And so if a distribution is symmetric, single-peaked, and bell-shaped, the distribution is considered to be normal. Now, we also have the empirical rule, which the empirical rule is just that 68, 95, 99.7 rule. If a data set follows a normal distribution, and in that case, then 68% of our data would fall between one standard deviation of the mean, or fall within one standard deviation of the mean. 95% of our data would fall within 2 standard deviations of our mean, and 99.7% of our data would fall within 3 standard deviations. So if we kind of give that a visual representation right here, we know that this represents a normal distribution. 68%, or the heart of our data, is going to fall within 1 standard deviation of the mean, 95% would fall within 2 standard deviations, and 99.7 would fall within 3 standard deviations. This image is also super useful, as it kind of tells us, if we're asked how much is this data above, or at what point, how much of a percentage above the mean is this particular data? Well, I really don't need 68%, which represents either one below or one above. I would only need one above or two above. So I can kind of split my percentages up, essentially, between, like, saying, one standard deviation above the mean represents 34% of our data, or two standard deviations above the mean represents 13.5 plus 34% of our data, so on and so forth. And then these two little tails right here are represented by 0.15% of our data right there. So if we're given an example for this empirical rule, suppose that taxicabs in New York City are driven an average of 75,000 miles per year with a standard deviation of 12,000 miles. What information does the empirical rule give us? Well, what that gives us is that, assuming the distribution is bell-shaped, we can conclude that approximately 68% of the taxis are driven between 63,000 and 87,000 miles per year. Because we're looking at 68% of that, what we know is that that's going to be one standard deviation below and one standard deviation above the mean. So we would take our standard deviation value of 12,000, subtract it once from 75,000, and then add it once to 75,000 to give us 63,000 and 87,000 miles per year. So that's how we know that those two values are representative of one below and one above the mean, or one standard deviation below and one standard deviation above the mean. You could do the same thing for 95 and 99.7%. So approximately 95% are driven between 51,000 and 99,000. So this would be two standard deviations below and two standard deviations above the mean. And virtually all are driven between 39,000 and 111,000 miles. So three standard deviations below the mean and three standard deviations above the mean. Okay, when we're looking at this idea of box plots, for this example, after an AP statistics teacher hears that every one of her 27 students received a 3 or higher on the AP exam, she treats the class to a game of bowling. The individual students' scores are as follows, all of those scores. So if we're looking at a box plot and we're trying to read this, essentially we need to know a couple things. First, we need to know these 2 points right here. Both of these, this one's going to represent the minimum point, this one's going to represent the maximum point. We also need to know this right here. This represents quartile 1, this represents quartile 2, and finally this represents our median right there. So each one of those lines or points on that box and whisker plot represent values, essentially, in that 5-number summary. So we would say that the minimum's probably somewhere around 70 or something like that. Our maximum would be somewhere around 220. Yeah, probably somewhere around 220. Whereas quartile 1 is going to be represented by about 160, and quartile 1, is going to be represented by about 100. Quartile 3, and this should be quartile 3, sorry, not 2, quartile 3. Quartile 3 is going to be represented by about 160, and our median is going to be about 140 in this case. We also need to understand what changing units does to our center and spread. So changing units, for example, from dollars to rubles or from miles to kilometers is common in a world that seems to become smaller all the time. It is instructive to note how measures of center and spread are affected by such changes. Adding the same constant to every value increases the mean and median by that same constant. However, the distances between the increased values stay the same, and so the range and standard deviation are unchanged. So how do our operators, our mathematical operators, affect our mean and median, or our standard deviation, our spread, basically? So if we're given this example right here, a set of experimental measurements of freezing point of an unknown liquid yield a mean of 25.32 degrees Celsius with a standard deviation of 1.47 degrees Celsius. If all measurements are converted to the Kelvin scale, what are the new mean and standard deviation? Well, if we're going to convert from Celsius to Kelvin, that's essentially just taking the Celsius value and adding 273.16. Well, you'll notice that our average degrees in Celsius is 25.32. So because we're just adding all we need to do is we just need to add that value to our mean, and that gives us a new mean in Kelvin of 298.48. However, because we're only adding values, we're not changing how far apart they're spread, our spread is essentially just going to stay the exact same. So when we add or subtract values to our mean, our center does not change at all. Our mean, median, whatever it is, it's not going to change. However, our spread, if we try to add values to that, that is not going to change at all. So our center is going to change by whatever values we add or subtract. Our spread is not. When we multiply, though, and divide, that's different. So in this example, measurements of the sizes of farms in an upstate New York county yield a mean of 59.2 hectares with a standard deviation of 11.2 hectares. If all the measurements are converted from hectares, the metric system, to acres, 1 acre was originally the area a yoke of oxen could plow in one day. What are the new mean and standard deviations? So because 1 hectare is 2.471 acres, we essentially have to multiply our values of center and our value of spread. So because we do that, we have to apply that to both the center and the spread. So we would take the mean and multiply 2.471 to find our new value, and the standard deviation, multiply that by the new value, and we would get our new value right there for that. So adding and subtracting changes the mean and median, does not change the standard deviation. If we're multiplying or dividing, that does change both the mean and median and standard deviation as well. If we have to do both in one problem, then we need to know what it is that we need to change in order to find our new values. So suppose we wanted to change the temperature from a study in Celsius to Fahrenheit. We know that the mean is 12 Celsius and the standard deviation was 2 Celsius. What is the mean and standard deviation in Fahrenheit? So our conversion equation is that if we need to convert to Fahrenheit, that's going to be 9 divided by 5 times the Celsius plus 32. So because all areas of mean or center are affected by both multiplication and addition, then we have to just plug our degrees Celsius, or our mean degrees Celsius, into our formula and then just solve. So 9 divided by 5 times 12 plus 32 gives us a new Fahrenheit value of 53.6. However, our standard deviation, because it is not affected by addition or subtraction, all we are doing is the multiplication part. So that would just be 9 divided by 5 times 2, which gives us a new standard deviation value of 3.6 degrees Celsius. So to kind of wrap it all up, the two principal measurements of the center of a distribution are the mean and median. The principal measurements of the spread of a distribution are the range, the maximum value minus the minimum value, the interquartile range, which is quartile 3 minus quartile 1, the variance, and the standard deviation. Adding the same constant to every value in a set adds the same constant to the mean and median, but leaves all the above measures of spread unchanged. Multiplying every value in a set by the same constant multiplies the mean, median, range, IQR, and standard deviation by that constant. The mean, range, variance, and standard deviation are sensitive to extreme values, while the median and interquartile range are not. That's why we try to use median and interquartile range for when we're describing center and spread of a distribution. The principal measurements of a position are simple ranking, percentile ranking, and the z-score, which measures the number of standard deviations from the mean. The empirical rule, or the 68, 95, 99.7 rule, applies specifically to symmetric bell-shaped data. So this does not apply to any other distribution. It doesn't apply to a left-skewed or a right-skewed distribution, only to a symmetric bell-shaped normal distribution. In skewed left data, the mean is usually less than the median, while in right skewed data, the mean is usually greater than the median, because we have values in a left skewed that are far less than what the median would be, so it would skew our mean. It would make our mean less than our median, whereas in a right skewed data set, we have values that are way higher than our median, and so that's going to drag our mean to the right or make it higher as well. Box plots visually show The 5-number summary, the minimum value, the first quartile, the median, the third quartile, and the maximum value, and usually indicate outliers as distinct points. We also note that 2 sets can have the same 5-number summary and thus the same box plots, but have dramatically different distributions in this case.